So it's been a couple months now since you first were introduced to the concept of an antiderivative. And the very first question I asked you was to list three functions whose derivative is 2x. So the day I introduced this, that was the very first exercise. And for some of you, you immediately thought of x squared and then said, well, what other functions could have the same derivative, right? And then we realized it could be x squared plus 1, x squared plus 2, x squared minus 10, x squared plus 5,225, right? Anything. Okay, so that's where we've gotten to this notion of, don't forget to add a constant, because if I were to graph, right, all functions whose derivative is 2x, right, they would be any function x squared, right, but shifted horizontally, right? They'd all be horizontal shifts of one another. And what we can see then is if we draw tangent lines to the curve, which is what I did on this next page, I came to the value where x equals 1. And let me see if I can put a nice vertical line at x equals 1. So notice what's happening when x is 1. I drew tangent lines to the curve, right, at these three different curves, right? One of them's x squared, one of them's x squared plus 1, one of them's x squared plus 2. And what we can see is that the tangent line drawn to the curve at x equals 1, those tangent lines are all parallel. Okay, well, we know parallel lines have the same slope. So that helps verify for us that no matter where the function is horizontally on our x and y plane, we have the same derivative at a certain x value, right? No matter which curve we are looking at, okay? And I could have put tangent lines at every other curve that I drew, and we'd see that all the tangent lines are parallel. So coming over here, if I wanted to find the actual curve that I started with, okay, so there's an infinite number of curves that have the derivative 2x, okay? If I give you what is known as an initial value, so that is why these are titled initial value problems. If I just give you an initial value on the curve f of x, then you know out of the infinitely many possible horizontal shifts that I could have here, if the point 1,3 lies on the curve, so if I can locate that, here's the point 1, let's see, I have to get up a little bit more to get to the next curve, or to get to the proper curve. The point 1,3 is right here. Okay, so if I know one point on the curve, then that can allow me to narrow the curve down to one single curve out of infinitely many. So in this case, the constant would have had to have been 2. So I can see that on the graph, but normally we don't graph the functions to see that. So then I do this algebraically. So then I say, okay, if I want to find f of x, right, f of x is the antiderivative, f of x equals the antiderivative of f prime of x, which is 2x. I'm sorry, I meant to write just 2x. 2x dx, right? Which I know is x squared plus a constant. Okay, so f of x is x squared plus a constant. And then I'm told if x is 1, right? This is x, right? Well, the functional value has to be 3. So I plug in 3 for the f of x, okay? 1 for x, and solve for the constant, okay? Thereby giving me what I already could see on the graph, that the constant is 2. Okay, so then I, for my final answer, would write y equals, or f of x equals, x squared, x squared plus 2. Okay, so let's look at one more of these examples. So let's actually come down here, and the derivative of some function is sine x. Okay, so again, if I want to find f of x equals the antiderivative of sine x, okay, which we know that to be sine x dx. We know that to be positive cosine. Okay, so positive cosine plus a constant. Okay, so then I'm told, well, the functional value at pi over 3, sorry, this was, I must have had inverse trig on my mind here. This is incorrect. I just paused the video and changed it. But anyways, so f of pi over 3 has to be 5 over 2. So if I input pi over 3 for x, right, and then I solve for the constant. So let's see, cosine of pi over 3, that's 60 degrees. We need to know these values. So this is 1/2. Okay, so we get 5/2 equals 1/2 plus c. Well, let's see. So 5/2 take away 1/2 is 4/2, right? And 4/2, of course, is 2. Okay, so I declare my final answer as f of x, or y, equals cosine of x plus 2. Okay, and as I showed you the last time, here's a couple of the infinitely many functions who would have sine as their derivative, right? These are just a couple shifts of the cosine curve. And if I came down here and I did a screenshot, so pi, remember pi is 3.14, pi divided by 3, so it's about 1, right? And so I did locate this curve, this point, or pretty close to the point. It was hard to get to it exactly, but this is approximately the point where I can see that if I input pi over 3, which is about 1, I output 2.5, which is approximately 5 over 2.